Okay, so today we're going to do sound and intensity, and obviously today is April 16th, not like I said the other day was. I had to change the order of my lectures a little, sorry. So today is actually April 16th, which is my birthday, okay? So we're going to do sound and intensity. So sound is a compression wave, so like a slinky, okay? And so it's a mechanical wave, so it does require a medium. It's not like an electromagnetic wave, which is a transverse wave, where it doesn't require a medium. This requires a medium, which means a solid, liquid, or gas, okay? So it needs a medium to travel through, like a solid, liquid, or gas. The speed of sound depends on several factors. So temperature. So all sounds travel faster at higher temperatures. So the hotter the day, the faster the sound travels. So the way that sound works is particles have to hit other particles to transmit sound energy. So if you have higher temperatures, you have more particles running into each other more often. Okay, so your collisions will be more often, so the sound can travel through particles faster. Mediums. So they travel fastest in solids. So think about like when there's an earthquake, there's an epicenter of the earthquake, like deep, deep underground, and it travels so fast that there's almost no warning between when the first little bits of vibrations are felt to when the huge vibrations are felt, which is why we can't really predict when there's going to be an earthquake coming to the surface of Earth, because it starts so far below, but it travels really, really fast. So that's because the particles in a solid are packed very close together, so they transmit that energy super duper fast. Liquids, they're not as close together, so they don't travel as fast. And of course, in like air, particles are very far apart because that's a gas. So it travels the slowest in a gas. All right, sound also exhibits certain wave behaviors. So there's 4 different wave behaviors that you need to know about. So they have interference, which we've already talked about, which is when you have a wave plus another wave makes a new wave. So it can make a wave of higher amplitude if they add together, so constructively, or they can make like a jumble or no wave at all if they add together destructively. There's a reflection, so waves can reflect or bounce off of other surfaces. That's like what an echo is a reflection of sound. They can refract, which means bending due to a change in the medium. So like an ultrasound is, it is a picture, but it's generated from it's generated from sound bending around different things that are seen on the whatever you're looking at, what your thyroid or a baby or whatever. And I realized I forgot something here. So diffraction is when the waves spread out. And so example would be like hearing around corners. Sorry, hearing around corners, that's hard to read. All right, the range of human hearing. This is really important, you need to memorize this. The range of human hearing is 20 hertz to 20,000 hertz. So that's the frequency that you can hear. So this is not the lowest frequency that exists. That's the lowest frequency that a normal human can hear, okay? And this would be the highest frequency that a normal human can hear. Typically, as you age, this number will come down. So like I'm in my 40s. I'm not gonna tell you how old I am today, but I'm in my 40s. And I cannot hear in this range at all. Like my hearing can go up to maybe 15,000 hertz, and that's about where it stops. So as you age, this number will come down. This number you can probably still hear. It's a pretty low frequency sound. Like remember, low is how high pitched or something is. So this is like really low pitched, and this is really high pitched. So really high pitched sounds you can't hear as you get older. That's just a normal thing. Wear and tear of your ears, that sort of thing. All right, so we have some calculations that we have to know about. So you have two different formulas that you're going to have to know, and they are, in fact, on your formula sheet. And again, they're on the back, like everything else that we're doing for this unit of your formula sheet. So you have, let's see, there's the, that's the absolute intensity formula, and this is the intensity level or relative intensity formula. Okay, so when you're looking for sound intensity, the intensity is the power over area. So we don't really have to use this so much to calculate anything, but that's kind of what it means. So it's in watts per meter squared. The I naught, this is your threshold of hearing. This is the quietest sound that you could possibly hear, okay? So it's the very quietest that you could possibly hear. The intensity level, this is the relative intensity. This is what normal, like, things are measured in as far as sound. Like if you have a stereo, it's probably in decibels. So decibels is your intensity level, and it's basically how loud something is. So your intensity level is kind of, it's a variation of this to try to get the B out of here. So it's logarithmic because you have something in an exponent that you're trying to pull out of an exponent. So this is the formula for that, but they have the same stuff in them, okay? The same variables, they're just in a different arrangement, that's all, okay? So this is the one that we use more often. This one is just to figure out how loud something is, so it relates it to a number that makes more sense to a human being, okay? That's really all this is supposed to do. All right, okay, so let's talk a little more about how loud things are. Okay, so loudness. So louder sounds have more amplitude, so they have more energy. So louder sound waves have more energy. And so when we measure that loudness in decibels, like I said, it's decibels, again, is just a way to make things in a number that's more easily understood, like a 0 to 120 kind of a thing. The decibel scale is logarithmic. So twice the intensity, the I, is not twice as loud, okay? So the way that we would relate that 10 times the I is 10 decibels, and that would be twice as loud, okay? So, for example, if I had, there we go. If I had 100 times I, that would be about 4 times as loud. Because 2 squared is 4, which means you have an increase of 20 decibels. So each 10 decibel increase is twice as loud. So a 20 decibel increase would be 4 times as loud. If you had 1,000 times I, that would be 8 times as loud. Okay? And that's because 2 to the 3 equals 8. So this is to the 3rd, this is to the 2, okay? Which would mean you have an increase of 30 decibels. So 30 decibels is twice as loud as 20 decibels. Okay? All right, so now let's use those equations in a more practical way, like how you're going to use them on your homework. Okay, so this is more conceptual than it is math, which is, you need to know that. Okay, so a person speaks with an intensity of 1 times 10 to the negative 7th watts per meter squared. Okay, so that's your I, that's your intensity. Let me change colors of pen, make it a little more obvious for you. If I can find a good one. There we go. All right. So So this right here, this is your I. I want to know how loud is this person. So I want to find the intensity, the relative intensity, the intensity level, okay? And then I want to know how loud would 30 of these people be. Okay, so that's another intensity level. So let's do part A first. So I know that my intensity level is 10 times the log of I over I naught. So that'd be 10 times the log of my I is 1 times 10 to the negative 7th over I naught, which is 1 times 10 to the negative 12th. So stick that in our calculator. Which I haven't pulled out of my desk yet today, sorry. Okay, so 10 log 1 times 10 to the negative 7 divided by 1 times 10 to the negative 12. Okay, and you get 50. So that person is 50 decibels. That's how loud that person is being. Okay, now, if I want 30 people, okay, so I'm going to tell you this, it's at the bottom, but never manipulate intensity level. So I wouldn't do 30 people times 50 decibels. That's not how loud 30 people are. That would be ridiculously loud. That's not how loud they are, okay? So what I'm going to have to do is I'm going to have to manipulate my intensity, my absolute intensity, the I, and then work with the B to figure out the intensity level, okay? So for part B, so my new I is 30 times 1 times 10 to the negative 7, okay? Which is 3 times 10 to the negative 6 watts per meter squared. So that's my I, okay? So I changed my I. 3 times people with this intensity, absolute intensity, gives me this. This is the intensity of 30 people. So now I find how many decibels those people are. So it's 10 times the log of 3 times 10 to the negative 6th over 1 times 10 to the negative 12. Okay. So that's 64.8-ish decibels. Okay. So they are louder, okay? They are more than 2 times as loud as this one person, which makes sense, okay? They're more than twice as loud as one person, okay? But they're not 30 times louder. Does that make sense? They're not 30 times 50, right? They're twice as loud. Well, a little more than twice as loud, right? Okay, so anyway, all right, so that's how you use those formulas. So, do your homework.